Hello, everyone. This is Hongwei Zhang. I'm a professor of computer engineering at Iowa State University, and I lead with many other colleagues and partners this ARA Wireless Living Lab project. So here I'm going to give an overview of the ARA project and also share some of the latest status. So, the primary objective of the ARA project is to enable research and education in rural broadband, especially focus on try to focus on the technology elements that may still need to be investigated to bring affordable rural broadband to everywhere in the rural regions. So as we develop these technologies, one of the key factors to look at is actually make sure that the cost is actually very low, right? For example, we are looking at a cost of reduction of a factor of 10 or more compared to today's solutions, because that's actually what's needed to make rural broadband as affordable as urban broadband in the US. For example, in US, the typical population density in the rural regions is going to be 10 by a factor of 10 or more less than the urban population density. That's one of the rationale there. Now, as we look at the technology elements for the rural broadband solutions, we want to look at, of course, how to connect the rural communities, but also we want to look at the needs of the rural industries, such as digital and precision agriculture. So with that in mind, the ARA Living Lab is being deployed in central Iowa. The deployment actually covers, I expect to cover an area of a diameter up to 36 miles or about 60 kilometers. And so what this map shows here is the what we call the backhaul, the ARA Hall sites that's spanning several up to 6 cities, and also the research farm at the ISU camp around the ISU camp outside the ISU campus. So what you see here is a mesh network of high capacity long distance wireless links that form this wireless high capacity mesh network, and at each site, we also deploy advanced wireless access platforms. And then in the city of Ames, where ISU reside, we have a little bit denser deployment of the access network across the Curtis Farm, Wilson Hall, and ISU Research Park, where the research centers of John Deere, Vermeer, Collins Aerospace, and other companies also are co-located. So with, by the way, there's also the U.S. Farm Progress Center that's somewhere between the city of Boone and Ames. That's going to be within the coverage range of the ARA network. This is a show center that where once every 2 years, the major solution providers and also customers would come here. It's one of the largest events in the ag industry, ag tech industry. There's also going to be a producer farm that's going to be within the ARA coverage range. Now, with a sharp focus on the needs of rural industries, the deployment would actually feature state-of-the-art crop and livestock farms, as well as including the farm facilities such as a green mill, biorefinery, also the large ag vehicles, robots, drones, cameras, and sensors that may be deployed in these farms. So there's also environmental sense and control facilities and also solar farms that can be potentially leveraged in experiments. We also have a good focus on the use case of rural communities. So therefore, the deployment is also going to feature rural facilities such as water towers, public safety vehicles, fire trucks, police cars, school buses, as well as municipal airport. Within the ARA footprint, there are 2 municipal airports that can be used to fly large drones for drone-related research. Now, let me actually elaborate a little bit about some of the technology elements. So for the long distance high capacity wireless backhaul solution, the ARA, it features a diverse range of high capacity platforms ranging from the free space optical link to microwave, the 70, 80 gigahertz band, and the microwave. And in particular, this free space optical system, ARA Optical, is being developed as part of the project. And once completed, it's expected to offer over 100 gig BPS capacity at long distance, for example, up to more than 15 kilometers. That's on the backhaul network. And then on the access network, this is where you can find 5G and beyond solutions from the state-of-the-art 5G massive MIMO and millimeter wave solution from Ericsson to fully programmable SDR systems using, for example, NI, N320 SDR for the base station and also B210 for the user equipment. We're also working with Skylark Wireless in bringing high capacity programmable massive MIMO solutions at low UHF, the TWY baseband, so that it offers both a production quality solution, but also with it has rich APIs that the research and education community can leverage. Together, the ARA system actually covers a wide spectrum range. For example, if you look at the software-defined radios, it covers a lot of frequency band at below 7.2 gigahertz. Now, for the long-distance communication, right now the RF front end is configured to support TWY space, mid-band 3.4 to 3.6 gigahertz, and also as part of another project, the National Radio Dynamic Zone project, we may well be able to support 5 gigahertz UAV band. And then there's also the COT solutions, such as RF sensors that can cover the sub-6 gigahertz, and also the base stations, the access network and base stations, UEs, and the ARA Hall radios that give us a diversity of frequency coverage so as to enable really interesting spectrum innovation experiments too. Besides its own state-of-the-art platforms, the design of ARA is such that it can support experimenters to bring their own devices. What ARA would offer in those cases would be those really useful infrastructures and software support so that experimenters can just bring their device and plug and play, be able to use it. For example, we are currently actually collaborating with Microsoft Research in integrating their TWY space IoT platforms into the ARA for potential IoT kind of experiments. So we have been working on this for some time, and we are actually in the process of wrap up the phase 1 deployment around the state of Ames and surrounding crop and livestock farms. In particular, we have deployed all the access network equipment at the Wilson Hall, Curtis Farm, Research Park, Agronomy Farm, as well as the high capacity multimodal wireless link solutions that's between the Agronomy Farm and the Ames Wilson Hall. So here are some photos showing the deployment. This is a tower at the Agronomy Farm, the rooftop deployment around the Wilson Hall of different kind of radios. This is Aviat E-band and microwave link, and then the ARA optical telescope here. And so that's on the base station equipment and the backhauling. We have also been deploying the user equipment across the farms and cities so that the community can access both the user equipment and the base station for experiments. So here's showing some figures in the deployment in the farms and so on. We have actually done some preliminary study just to give the community a little bit insight into the behavior of these systems. For example, for the Aviat 11 gigahertz and 80 gigahertz wireless X-Hall solution, So far, we have observed aggregate capacity over 8.6 gig BPS at a distance up to 6.4 miles. In a way, for example, actually, this is a first of its kind experiments that's done for the 80 gigahertz link at such high long distance, actually. We have seen that we have also observed that the weather would actually have impact on the higher frequency band links. For example, there's actually about 20 dB of signal loss for the 80 gigahertz link. However, the 11 gigahertz link would be much more robust. So there's actually the spectral diversity there that you can see. So that's actually one dimension that we can leverage to build robust high capacity links as part of the experiments. So that's on the ARA Hall. And the access network part for the Skylark massive MIMO solution, we have observed a throughput of over 100 Mbps capacity at 24 with a 24 megahertz channel, and also up to coverage up to 6.36 miles with decent throughput. This is still being debugged. We do expect to see higher throughput over time. We also see that because the Skylark system is operating at lower frequency band, the performance is actually insensitive to the weather impact, as you can see in these figures. For the COTS massive MIMO solution, massive MIMO and millimeter wave solution for Ericsson, we have done some very preliminary study at this point, and the result looks very promising. For example, we have observed for the research park site that's actually just right next to the John Deere Technology Innovation Center. We have observed an aggregate throughput over 3 gig BPS up to 300 meters. And then for the mid-band radio, we have also observed up to 600 Mbps capacity at a distance over 1 mile range. Now, in general, the ARA can support a wide range of interesting research studies, including, for example, long-distance high-capacity wireless xHaul. That's absolutely needed for the rural broadband systems, and also the low band, the TV white space massive MIMO systems with programmable production quality implementation. In addition, we have fully programmable SDR-based cellular base stations, UEs, and also the COTS 5G massive MIMO and millimeter wave systems. Besides wireless communications and networking, ARA does provide edge, fiber, and also cloud resources so that it can also support end-to-end experiments that involves wireless, fiber, edge, and cloud. There's also actually a very good focus about application research, because we do feel that being able to put wireless experiments research in a specific context to actually help drive progress and innovation. So here are some, I just listed a few canonical agriculture and education applications. So we are looking at, in particular, for example, there's a use of a robot for high throughput phenotyping. By the way, this robot can actually generate data at a throughphut of over 3 gig BPS, actually about 2.4 to 3 gig at the highest resolution. Similarly, in agricultural automation, that's where so you can see there's the need of streaming high resolution imaging and sensing data to the edge for real-time processing, and then drive real-time control into the field, for example, for weight control. Right? There's also the use of camera systems for precision livestock farming, also the use of XR for ag education that folks can look at, can explore in the ARA systems. So that's a high-level summary of ARA, hopefully to give you some insight into what ARA can enable. To stay updated about the progress of ARA or events, please do join the ARA users Google group. We have a Google group that we use to communicate. We also have LinkedIn webpage that you can look at. To reach out to us, you can also email us at e2@arawireless.org. So on the arawireless.org website, there's actually a lot of information you can look into. For example, if you come here, you can actually find detailed information about the deployment. You You can also navigate the map to see what kind of equipment is there. And also, there's actually some discussion of the specific equipment, the type of research that can be enabled, from wireless research to application ag research, and also the detailed information about how you can actually get hold of us. There's actually the ARA portal that you can use to actually run ARA experiments. So with that, we'll stop here, and thank you for your time, and look forward to working with you. Thank you. Bye.